Hi, this is Lakshmanachari, working as an assistant professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss problem solving on memory management. So, in the digital computer system, mainly it has three essential components that are central processing unit, memory subsystem, and I/O subsystem. So, CPU, central processing unit, it performs all various operations. That means the CPU, again, it consists of internally three essential parts that are ALU, arithmetic and logic unit, control unit, and the registers. So ALU, it performs arithmetic and logical operations, like arithmetic operations are addition, subtraction, multiplication, division, and logical operations are AND, OR, XOR. So the ALU, it performs all these arithmetic and logic operations. So after that, the memory subsystem. So memory subsystem, it is a very important, it plays a very important role in digital computer system, because the memory unit is an essential component, because inside the memory we are storing various programs and the data, and a very small computer with a limited application may be able to fulfill its intended task without the need of additional storage capacity. So that means a small computer with limited memory, it can able to fulfill its intended task. But if it wants to perform very large applications, then it requires some additional storage capacity. So most general purpose computers would run more efficiently if they were equipped with additional storage behind the capacity of the main memory. So already we know in the digital computer system, the main memory is a limited memory. So we cannot store the large amount of data or programs inside this main memory. So that's why in addition to the main memory, we are using some additional storage capacity. That means that are auxiliary memories or secondary memories. So in that auxiliary memories or secondary memories, we are storing all the unused programs and data. So only the used programs and data will be copied from the auxiliary memory to the main memory whenever it requires, or whenever that programs are to be executed. Then only the content will be copied from auxiliary memory to the main memory. And if you run any application or if you open any files, all that files will be opened from the main memory. And coming to the memory management. So memory management is the process of the controlling and coordinating the computer's main memory. So that is called memory management. So it ensures that blocks of memory space are properly managed and allocated to so the operating system, applications, and other running processes have the memory they need to carry out their operations. So the memory is very important and it is required to carry out all various operations inside the computer. So this is a memory hierarchy in a digital computer system. So that means here we can see all the various memory devices which are associated with the CPU. So this is a CPU, central processing unit. So different memories are associated with this CPU, that are cache memory, main memory, and the auxiliary memories. So auxiliary memories are the secondary storage devices, storage memories. That means all the large amount of data, unused large amount of programs and data that are stored in the auxiliary memory. And some of the examples of auxiliary memories are the magnetic tapes and magnetic disks. So these two are operated by the I/O processor. So that means the I/O processor is a special type of processor that can perform all the operations related to the input or output of the memory devices. That means input or output operations of the I/O devices. So after that, main memory. So main memory, it can be, the RAM can be treated as a main memory. Okay, and the secondary memories are the ROM memories, and this is a main memory. So main memory is a volatile memory. Main memory is a volatile memory, because if the power fails, then the data stored in the main memory gets erased. But whereas in the ROM is a non-volatile. It is a non-volatile memory. That means even the power fails, the data stored in the memory will not erase it. So that is the main advantage with the non-volatile memory. And after that, cache memory. So cache memory is it is very faster. It is the fastest memory, and but it has very small amount of storage capacity. So this cache memory in the computer, it will increases the speed of execution of the processor, because when the CPU access, if the CPU wants to access any data, first it checks in the cache memory. If that requested data is not available in the cache memory, then it will search in the main memory. Even the data is not available in the main memory, then it will be searched in the auxiliary memory. Okay, so suppose if the requested data is available in the main memory, so while accessing the data from the main memory to the CPU, a copy of that will be placed in the cache memory also. So when the CPU requested the same data again, then the CPU will not go to the main memory directly. First it checks in the cache memory, then the CPU can access the data from the cache memory itself. So that's why, in this way, the cache memory can reduces the access time, so that it will increases the speed of execution of the processor. Because for the CPU, it takes very less time to access the data from the cache memory than the main memory. And coming to the ROM chips. So the computer's memory, mainly they are divided into two types. The first one is a ROM and second one is a RAM. So ROM chips, so we have different types of ROM chips are there, and these are differentiated by how often they can be programmed. So how often they can be programmed, based on that the ROM chips are classified into various types. The first one is the masked ROM. So this masked ROM is it is oldest type of the memory, and in this the content was stored by the manufacturer and not by the user. So the user is not able to modify the content, modify or reprogram this type of masked ROMs, because once the manufacturer loaded in the program into this masked ROM, the user cannot alter it. Okay, so the example of the masked ROMs are the memory devices which are available in the home appliances, like if you consider microwave oven, refrigerator, air conditioner. So these are all. So because there is a memory inside that devices, that means the program which is required to operate the device will be loaded by the manufacturer. Once the manufacturer is loaded, as a user, we cannot modify the program. And after that, PROM, programmable read-only memory. So the name itself, it specifies the meaning. Programmable read-only memory. That means the user can, the empty PROM chips are available in market. So the user can purchase a empty memory chip, PROM chip, and it can be programmed by using a PROM programmer. Programmer is a device. Using that, we can load the program into that particular memory chip. So here in this PROM, the user can load the program only one time. Only one time programmable. Once it is programmed, the user cannot modify or reprogram it. And after that, EPROM, EP, erasable programmable read-only memory. That means using this EPROM, the user can program and erase multiple times. That means the user can load the program, then they can test it, then they can erase it, again they can load. So like that, multiple times programmable and erasing is possible in erasable programmable read-only memory. And coming to the EEPROM, in EEPROM, electrically erasable programmable read-only memory. That means here in EEPROM also multiple times loading, multiple times writing the program and erasing is possible. That means approximately 10,000 times programmable and erasable. And last one is a flash EPROM. So this flash EPROM is advanced than EEPROM. Okay, so it is advanced of EEPROM, flash memory. Coming to the RAM chips. So the RAM chips are differentiated by how they maintain their data. So that means in the RAM chips, how the data is stored. Based on that, the RAM chips are classified into two types. The first one is the static RAM and second one is the dynamic RAM. So in static RAM, the data is stored in the form of flip-flops. In the flip-flops, the data will be stored. Whereas in dynamic RAM, the data can be stored with the help of the capacitor and the flip-flop. So this is about the RAM. And coming to the problem solving, the question 1, if memory is having 12 address lines and 8 data lines, then find out number of registers per memory location and word length. So if memory is having 12 address lines and 8 data lines, then find out number of registers per memory location and the word length. So the number of registers per memory location, that is equal to 2 power n. So 2 power capital N. So where n is the number of address lines. So the memory capacity can be calculated using this formula, 2 power n. So that is equal to 2 power n. So where n is equal to 12. So 2 power 12. That means 4096. So 4096 memory locations are there in that memory device. And coming to the word length. So word length is equal to m bit. So already in the problem statement, this specified 8 data lines. That means the word length is equal to the 8 bit. So suppose if you have a memory like this, so that means total we have 4096 memory locations. So that means starting with 0 and ending with 4095, because the starting address is started with 0. So that's why n minus 1, 4096 minus 1. So 4095. So these many memory locations are available in the memory device. And the word size. Word size means word length, or word size means the number of bits we can store in each memory location. So that means here the data lines are 8. That means here we can store 8 bits of data. So the word length will be equal to 8 bit. Coming to the second question, find the number of address lines required if the memory has 8192 memory locations. So we need to find the number of address lines required if the memory size is given. Okay, so memory size is given 4192 memory locations. So here we have given a table that summarizes the memory capacity and the address lines required for memory interfacing. So the first column is memory capacity and the second column is address lines required. Suppose if the memory device is having 1 kilobyte for locations, that means 1024 memory locations, then it requires 10 address lines. Similarly, the memory device is having 2 kilobytes of locations, means 2048 memory locations. That particular memory device requires 11 address lines. Similarly, if the device is having 4 kilobytes, 12 address lines are required. If 8 kilobytes of locations are there, or 8192 memory locations are there, then it requires 13 address lines. So, for this problem statement, with the memory device capacity 8192 memory locations, we require 13 address lines. Similarly, for 16K, 32K, 64K. So, that means 8K. The memory size will be 8K. So, that means it will be in 2 power n. So, 8K is equal to 2 power 13. So, 13 address lines are required. And coming to the question 3, design 1K by 8 RAM using 2114 ICs. So, we have to design a 1 kilobyte by 8 RAM using 2114 ICs. So, 2114 IC is it has 1 kilobyte of memory locations and the word size is 4. So, that means we are going to implement 1 kilobyte of memory location with 8 word size. With 8 word size. That means we are increasing the word size. So, in order to increase the word size, we need to connect the memory chips in parallel. So, like this. So, this is the first memory chip. This is a second memory chip. Okay. So, we are connecting the data lines. Total we have 8 data lines after designing. So, D0 to D3 we are giving to the second chip. D4 to D7 we are giving to second chip. So, total this memory device, it consists of 8 data lines. So, D0 to D7. D0 to D7. Okay. In addition to that, some other control signals also given. So, CS bar. CS bar means a chip selection line. Chip selection line and the read or write bar. So, with the memory, we can perform 2 types of operations, whether we can read the data or write the data. For that purpose, they have given read or write bar. Okay, so this read write bar and CS bar are active low input. That means if we give low input, then only they will be operate. So the memory capacity can be increased by connecting 2 or more memory chips in parallel. This means that the address, data and control lines connected in parallel to all memory chips. So we can see the memory mapping. So for that, once you design the 1 kilobyte into 8 memory chip, its address range is address range. Address range means we need to determine the starting address of that memory chip and ending address of that chip. So starting address would be it has all zeros. That means initially the starting address will be all zeros. So 0, 0, 0, 0, 0 like that. And the ending address will be all ones. So if you convert into hexadecimal, so how we can convert that into hexadecimal? So by grouping 4 binary bits together, it will be converted into the hexadecimal. So this will be 1. Next this will be 1. So that means its equivalent hexadecimal value 0, 0, 0, H. Similarly, if you convert the ending address into the hexadecimal, this will be 4 bits we have to group together. So this will be 1, 1. That means we can append some zeros to the left side. So 0, 0, 1, 1. That means 3. 1, 1, 1. That means F. 1, 1, 1 means F. That means for this memory chip, the starting address will be 000H2 3FFH. Coming to the fourth problem. So how many 128 by 8 RAM chips are needed to provide a memory capacity of 2048 bytes. Next, how many lines of the address bus must be used to access 2048 bytes of memory? How many of these lines will be common to all the chips? And the third one is how many lines must be decoded for chip select? Specify the size of the decoder. So let's see how we can solve this problem. So first one is how many 128 by 8 RAM chips are needed to provide a memory capacity of 2048 bytes. So already we know the required memory chip size and the memory size of that we are going to design. So we are going to design a memory capacity of 2048 bytes. So 2048 bytes by, and the available memory chip size is 128. 120. So this is if you write in write the data size also, data bit size also, 2048 into 8. This 2048 is a number of memory locations and this is a word size. So 2048 into 8 by the available memory chip size is 128 by 8. So 8 gets cancelled. 128 16 2048. That means total we have we should have 16 chips in order to design a memory capacity of 2048 bytes. And second one is how many lines of the address bus must be used to access 2048 bytes of memory? How many of these lines will be common to all chips? So already previously we have seen how to determine the number of address lines required for the specific memory capacity. So here the memory capacity is 2048. 2048. So 2048 is equal to 2 power n. So where n is the number of address lines. So here, as per this, if n is equal to 11, then that is equal to 2048. So the number of address lines required are 11 address lines. 11 address lines are required in order to access 2048 bytes of memory. And here the available memory chips are 16 with the size 128 by 8. And chip size is 128 bytes. 128 byte means 128 into 8. So 128 is equal to 2 power 7. So 128 means 2 power 7. 128 is equal to 2 power n. So where n is equal to 7. So that means 7 address lines are common for every chip, memory chip. So 7 address lines are required to address each chip and 4 lines are required to select the 16 chips, because total we have 16 chips. Using a decoder we can select all these. So using a decoder, so 4 input lines are there and 16 output lines are there. Using this, so every output of this 4 by 16 decoder will be connected to one memory chip. So this is a chip 1, chip 2, like that, chip 16. Coming to the third one, how many lines must be decoded for chip selector? Specify the size of the decoder. So 4 lines of decoder for selecting the 16 chips. So just before we have seen. So we need a 4 by 16 decoder. So that means 4 input lines are there and 16 output lines are there. Okay. So these are 4 and these are the 16. So total we have 16 chips. This is chip 1, 2, 3, 16. So for output, first output will be given to here. Second, third, last. So that by using these 4 input lines, we can decode. So in this way, the required size of the decoder will be 4 by 16 size. Okay, so the problems under the slides are prepared by referring the textbook M. Morris Mano, Computer Systems Architecture, publisher PSN, 3rd edition, 2015. And also refer John D. Carpinelli, Computer Systems Organization and Architecture, Pearson, 1st edition, 2001. So in this lecture, we have discussed various problems that are related to the memory management. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.